Okay. Well, we start in a couple of minutes. That I'm planning to show you today is the two other components of the lighting system. We'll start with drivers, ballast and drivers, and then we'll discuss also before lunch fixtures. This is the parts that constitute the system: lamps, fixtures, drivers, plus of course human being. Oops, no, it's not what I want to do. Okay, let's start. The others will arrive. Uh, the first talk then will be on ballast and drivers. Is someone between you knows what is the difference between a ballast and a driver? Pradium? No? Yeah. Well, in fact, there is no any kind of difference. Drivers are exclusively electronic devices. Ballast can be either electronic or ferromagnetic devices or any kind of passive devices also. But in fact, till 2017 or 18, for lamps and lighting, it was forbidden to use the word driver. Only the word ballast was standardized. And normally, even for LEDs, you had to speak about ballast. In fact, since that date, we decided to standardize also the word driver, and usually now we speak about drivers for LEDs and ballast for legacy systems. But in fact, it's exactly the same thing. It's just a question of standardization and terminology. We'll speak about standardization tomorrow. We'll speak extensively because lighting is one of the most standardized areas in this world, and it's necessary to understand what the standards impose for lighting. Okay. First of all, I am not a power electronics guy. Well, if you ask me very specific questions about ballast or driver topologies, I'm not sure that I can have the right answer, but I can find the answer somewhere and send it to you after. I will speak for both ballast for legacy sources because you will see that discharge lamps like fluorescent lamps or street lighting lamps, the old technology, they are very specific and they impose very specific constraints to the power electronic side. Drivers for LEDs, they are much more classic because an LED is a diode, and the only thing that it needs is stabilized current. Ballast for conventional lamps is much more complicated. In fact, normally each type of lamp, each lamp technology has its own power supply, okay? And the power supply must be adapted to the load at all times. Even if you have transients or during the warm-up of the lamps, for example, or how to switch on the lamp and things like that, the driver normally has to be well adapted to follow all those transients. It must ensure the nominal operation of the lamp when the lamp is stabilized. Must ensure, sorry, it's not priming, this is switch on. I don't know why I put the word priming. Most probably I was not in the best when I wrote that. It must ensure dimming, gradation effect, dimming of the lamps. in some cases, and it must comply, of course, this is compulsory, with any security, electrical hazard, or any constraint imposed by electromagnetic interference problems, and different other constraints. There are some factors that impacting directly the ballast design. The first one is the efficiency. How much energy you input to the ballast, how much energy will get before the lamp, sent to the lamp. The reliability. This is very critical, especially with LEDs, because LED itself has most probably much longer lifespan than the ballast. Compliance, electromagnetic compatibility, or standards IC 13000 concerning the total harmonic distortion. Today, all LED lamps have to comply with a standard that says no more than 5% of total harmonic distortion, and this is regardless of the power. Before the revision of the standard, for LED with power is less than 5 watt, LED lamps with less than 5 watt, that was not an obligation. Today, all lamps, they have to comply with this limit. Of course, the dimensions and the weight is very important. You know that the old ferromagnetic ballast was very bulky and heavy. They don't should produce any audible noise. Can be the case in some case. They needed to operate in wide range, temperature, humidity, and what you can expect. Other, avoid flicker, because flicker can has very harmful effects to our well-being. Flicker induce fatigue to all of us. Flicker can reduce our visual performance, but flicker can go up to triggering epilepsy crisis in sensitive people, especially when the flicker is perceivable. But even if it is not perceivable, has incidence to our health. Avoid flashing the lamp at the end of its life. All of you have seen lamps outside or inside. They are almost dead, and the ballast try to ignite the lamp switch on, off, and then you have back and forward pulses. That is not good either for the lamp or for the ballast, of course. Automatic recognition of the power supply voltage. This is important. If you have a ballast or a driver, it's better to be adapted to any kind of plug voltage, 230, 120, or maybe in the future DC, why not? And automatic recognition also of the lamp type. Some of the fixtures, they can accept a different kind of lamps. It was the case with T8 and T12 tubes. We can replace some T5 tubes with LED tubes. It will be nice if we have a driver that is able to know what is behind and adapt the driver characteristics to the load. And of course, the cost. The cost is a very important parameter. If you want to produce affordable lamps for plug and play lamps that all people can buy and put to our homes, first, you don't have enough volume to put all the elements, and you need to get low price in order to be accessible by anyone. I remind you that an old incandescent lamps here in India shall cost us something like a few rupees or 10 of rupees. I don't know how much. In Europe was less than €1. Okay. An LED lamp today is in Europe is 2-3 euros minimum and not for very good quality lamps. That means here in India should be around 100 rupees, something like that. And the price of the lamp many times is not the price of the LED, is the price of the ballast today and all the integration behind. In fact, when I said each kind of lamp has its own power supply, its family of lamps, if you want. The old incandescent lamps, they are almost linear elements. They are ohmic resistors, even if the resistance can change with the filament temperature, but the filament temperature is almost fixed. They don't have ignition, priming, sorry for the word, I think it was when I made the translation, priming means ignition, I will correct the word. They don't have ignition problem. An incandescent lamp, you switch on, you send the current, the time to the filament to heat up, but it's very rapid. Actually connected to mains, any kind of mains, or in some cases for low voltage lamps, they can be supplied by DC low voltage power supply. Then you have the solid state lamps, LEDs, and other. These require DC and requires polarization. This is a constraint, and we are speaking here about low currents. We can imagine some lamps, LED lamps that can operate direct on the plug. You tell me this is not possible. Yes, it is possible. If you say that one LED is, let's simplify, say 10 volt voltage threshold, if you put and you have 110 volts in the plug, then if you put 11 LEDs in series, you have the same voltage. But LEDs, they don't like AC. But if you take 4 LEDs and you put it in bridge situation, they illuminate, but also they will redress the current. The idea is very bad, but you can find some lamps of that style that 4 LEDs, they are working as bridge without any filtering, and then you have strings of LEDs that adjust to the voltage. Of course, you take that lamp for 110 volt, you put it in Europe in 230, boom. Okay. Discharge lamps are the more difficult to supply because, as you will see, I will explain you that they are strongly nonlinear elements. Even if at a relatively low frequencies, when I say low frequencies, I'm speaking up to gigahertz, they have pure resistive behavior. Above gigahertz, they may have also inductive or capacitive behavior, and this completely changed the idea. They can operate in very wide power range. We have discharge lamps starting at few watts, and on the other hand, discharge lamps going up to 2,000 or even 5,000 watts. And they require, of course, a ballast, or if you want, a current source, because these devices operate exclusively in AC, but with stabilized current. They need a fixed current AC. For example, fluorescent lamps, they need 400 milliamps average or efficient current, but stable. Let's start with the case then of discharge lamps, which is the more complex to understand and to manage. I will get the pointer. Yeah. Well, I told you that an electrical discharge is a nonlinear ohmic resistor, provided that you stay at frequencies which is lower that we call the plasma frequency, and the plasma frequency is above gigahertz. What is the problem with the plasma frequency? I remind you, when you are outside and you make a call, or you heard your radio, FM radio, you can catch the emission even if you don't see the antenna. Why? Because you have the ionosphere, which is reflecting the electromagnetic waves above a given frequency. The ionosphere is a plasma. Inside the lamps they are plasma, but here we are a very high frequency, and this can change the direction of electromagnetic waves. Just to explain you why above a given frequency the discharge is no more ohmic, but becomes usually capacitive. Okay? Let's see what means that. This is a classic ohmic resistor, V equal Ri, Ohm's law, and this is a discharge. When it is ohmic, at a given frequency, this curve can change as function of the frequency. It's not the same everywhere. And here you have some noticeable points. For example, you have that here is the ignition spike. I will speak about that. And here, for example, say when your discharge is at point 8, you switch on ignition, and then the discharge starts to stabilize somewhere here. And when you are at that moment, at the point A, you have a behavior like a resistor, and the resistance value is the slope of the curve. Look, it's I versus V. That means if you invert, this slope is negative. The electrical discharge not only is a nonlinear resistor, but it's also a negative resistance. And later, when the discharge will stabilize, you see that you pass from that point here to that point here, and then the slope is still negative, but it is different. That means your charge change value during the warm-up and stabilization period. And of course, the power supply behind, remind that was one of the mission of the power supply, is be able to follow this evolution, including the ignition here. Breakdown. Okay, and the shape of the curve change as function of the power supply frequency. Why? Because inside the discharge there are different physical phenomena with different characteristic times. And one of the most slow of those phenomena is that we call the diffusion inside the plasma, and you have an associated characteristic time which correspond to almost few kilohertz. That means this curve here that is like that during when the frequency is below the diffusion characteristic time, below 500 hertz to 1 kilohertz, and when you go above 1 kilohertz, this curve becomes linear like a resistor and can change again. And this is much more problematic, because if you design your driver for low frequencies, the same topology is no more valid for frequencies above kilohertz. Okay? Because the load change the electrical behavior. Okay. And you can see the linear effect, non-linear effect here. You see this is the supply current, AC. Whatever is the value here, could be a few hundred milliamps, sorry, for fluorescent lamps, can be up to several amps for high pressure lamps. It depends on the power. And if you are less than the characteristic time for diffusion, then look here, the form of the wavelength. You have that we call here the reignition peak, and this variation here is imposed by the VI characteristic of the discharge. Here is the discharge itself imposes some harmonic distortion. But now if you go above 1 kilohertz, then your discharge becomes again the linear, and you have almost the same thing. The small vertical lines here is not real, it's just when I plot my graphic, I forgot to join the two values in the intersection. It's an artifact. And there is another problem, which is not valid for the fluorescent lamps, but is valid for street lamps. Inside the burner, you remember the burner is the initial, the central part of the lamp. This is a burner of mercury high pressure lamp, but you can find the same. In a given frequencies, which are dependent on the chemistry inside, on the dimension of the tube, on the temperature distribution, and if you have some given frequencies, you excite that we call acoustic waves inside the lamp. The lamp may produce noise, but this is not a problem. The acoustic wave, they distort the form of the arc. And to give you an idea, in that lamp, the size here is 2 centimeters. The red part of the arc, the temperature here in such kind of lamp is something like 5,500 or 6,000 Kelvin, real temperature, it's not color temperature. And of course, the silica wall cannot afford more than 900 or 1,000 degrees C. That means if now your arc starts sneaking inside the lamp, the hot part of the arc will approach the wall, and if it is a silica wall, you don't see very well here, you can change completely the form of the tube. Here you can see that you have like bumps because the arc deformed the tube. But if you use ceramic is don't like thermal shocks, and boom. And here this is a metal halide ceramic lamp with an external bulb. This was 150 watt, small one, and just supply the lamp with the good frequency or the bad frequency if you want. We excite acoustic resonance inside, and you see everything gone in a very nice explosion. And even you see here that for the industry that was a very bad news, because even the external tube is not protecting from the explosion. Even the external bulb goes with the bang. Well, and the problem is those frequencies. In fact, here this is a real photo, but that you see inside is a simulation. It's a MATLAB code calculating the acoustic resonance frequencies. Those frequencies, they are depend not only on what is inside the lamp, but they depend on the geometry of the lamp, and they depend on the power also. That means what? If you overheat the lamp and the form of the lamp is distorted, then the frequencies may drift, or if you do dimming of the lamp, then the frequencies will drift again. And that means simply if you use a high frequency power supply, say above few kilohertz, then you make dimming, or I don't know what else, always you can be sure that you will have acoustic resonance phenomenon, and this is very bad for the lamp. That because this kind of lamps, we don't supply them at high frequencies, we stay in frequencies less than 500 Hertz at the best. Some very bad power supplies or ballasts, they go above 1 kilohertz for those lamps, but these kind of products, they have to be banned. They are very dangerous. And to save a little bit and increase I will told that later, to increase a little bit the efficiency of the power supply, instead of to send sinusoidal, that we are doing, usually we send square wave, but at low frequency. Yeah, this is the legacy ballast for the discharge lamps. The legacy ballast was what? Just a bulk inductor with a ferrite core. Here, if you calculate the apparent inductance, we are speaking about 1 point something Henry. It's really huge. And in fact, you have a voltage source here. You put in series a big inductance, almost infinity. And in fact, that you see from the lamp side is a current source. Okay, this is the reason why we call that ballast, because like in the ships, they keep the ship stable even if you have motion due to the waves. From there is coming the word of ballast. You have it here, and you see here also behind, we'll speak about that, a capacitor, which is to make some compensation. Well, look now what happened. Take the famous nonlinear curve here, okay? And then add here the characteristic of that part from A to B, which is the dot blue lines. First of all, you supply, the lamp plasma will break down, and then the lamp will continue to follow that. But the problem is that here, due to some inertia, the curve will go from here to here. That means all that area here, the lamp is in free situation. The ballast is no more following the evolution of the charge. You start the lamp, and you expect that to catch back the stable operating point after the end of the warm-up phase. And this is not good for the lamp, because if you leave the lamp alone here, you will damage mainly the electrodes inside. The electrodes will treated very badly. You will have a vaporization of the material, and if you damage the electrodes, of course you change the geometry of the lamp for the acoustic resonance, what I was telling before, but also you will reduce the lifespan of the lamp. And if you have that, if this is your arc current, everything is in series, then this is the arc voltage. I remind you that even if the curve is not linear, the lamp at any point behaves like a ohmic resistor. That is no phase shift. But you have to pass through the inductance, and finally that you see from I think I invert the letters here. You see a phase shift introduced not by the lamp, but introduced here by the inductance. And this cosinus phi here, today IEC standard says that we have to keep it less than 0.95 or 0.9, okay? Then you have to eliminate. The only way to do it is to add a compensator, a compensation capacitor here, and then of course, you can avoid. The problem is that these kind of capacitors, they are bulky and they are very sensitive to temperature, and their lifespan is usually less than 2 years. The lamp of the lifespan of the lamp is for street lighting is maybe 4, 5, or even more years in some cases. The lifespan of the ballast itself is infinity. It's just an inductance, but the lifespan here is very limited, and it's very unusual that cities replace the capacitance every 2 years. They never replace it, in fact. And what happened? Initially, your system has a good power factor, but after 2 or 3 years, the power factor of the street lighting system using this kind of ballast is absolutely catastrophic. That is the reason that for interior lighting in Europe we ban ferromagnetic ballast for fluorescent lamps since 1990. It's very old. We never ban ferromagnetic ballast for outdoor lighting, for street lighting, but during the last 2 decades, many people try to propose electronic ballast even for street lighting, but then you have different constraints and different other problems. Okay, let's continue. Yes, and also this kind of ballast consume also energy, because they are beyond the inductance. You have also resistor, and you use something like 15% additional power. If you have a lamp of 100 watts, the apparent consumption of your system, the consumption of your system is 15 watts. Okay. It's heavy and bulky, of course, and many of those contain lead, and lead is also very dangerous for the health. Now, if you look what happened with this kind of ballast and nominal operating conditions, here I invert the curve. I'm not looking anymore on the startup phase. This is the behavior of the discharge. This is the ballast. And you have 2 potential intersection points. That means you have to operate to that one or that one in order to have a stable operation of the lamp. But in fact, you have to look if the 2 points, they are stable or not, and the stability can be down by taking the small signal variation around the point, and that you can see is the slope of the curve should be the power supply should be bigger than the slope of the load, and in that case the 2 points here, only one is stable, only that one is stable, and you have to know again where is the stable point and calculate your power supply to fix the current. The power supply fix the current, and then the lamp choose its voltage. If you go there or there, what will happen is your system is unstable. Not only is unstable, but we can show mathematically that if you are here or somewhere there, nearby that one, you will go to higher currents, and if you go to higher currents, your lamp will explode. And nothing can limit. Above that, you go to higher powers. Between that and that, you can converge here, but the opposite, if you are above that point, can be very dangerous for the lamp and you. Okay? And that means that the impedance of the source should be always higher than the impedance of the load if you want to keep your system in stable conditions. Electronic ballast for discharge lamps. You understood now that ferromagnetic ballast is not the good option. we can use an electronic ballast, which is can be high frequency sinusoidal, and that can be used for fluorescent lamps or high pressure lamps, but in that case you have to go to very high frequencies in order to avoid all the region with acoustic resonance, and in that case the ballast becomes very expensive. Or for high pressure lamps, usually we use low frequency, not slots, low frequency wave, okay, square wave. Well, you understand here why this one is preferable, because if you supply your lamp with a current source that can change continuously, any point here can be followed by the evolution of the power supply here. That means that the ballast accompany the lamp in all transitory phase till the stabilization, and in that case the lamp is you have less risk for the lamp. Add to that this kind of power supplies, they are much more efficient. Usually they are composed to a rectifier, a filter that can be active or passive, and then an H bridge, or in some case a half bridge, in order to produce either square wave or high frequency sinusoidal wave behind. It is light and compact, and it respects the lamp because of the capacity to follow to a stable way at any moment the lamp behavior. Okay, there is electrical characteristics for some discharge lamps. You have to know that in order to size your driver or your ballast. Fluorescent lamps, they operate between 400 volts and 1400 volts that you need. The lamp can go from few milliamps to few milliamps. The ignition, you need high voltage. If you take high pressure lamps, here is a problem. It's 300, 800, sorry. I will correct it. High pressure lamps, the voltage is between 90 and 200 volts when the lamp is operating. You have from half ampere up to 10 amperes or even more. And for the ignition, you may need between 5,000 and 25,000 volts to ignite the lamp, because the problem is you have a gas, and you have to break down that gas in order to pass from gas to plasma, and the plasma the current passing through. And the ultra high pressure lamps that we use in such kind of projectors, they are very small. You see that they operate a low voltage but high amps, and the ignition is also even higher. You understand that? I will correct that one. I will do it even immediately, thus I will not forget it, sorry. Okay, it's better like that. Sorry, you are the very first that you see my new slide in English, and sometimes the things that there are some misprints. Well, I am correcting that. You see that any kind of lamp, especially the high pressure, impose very, very stiff constraints to the power supply. The case of fluorescent lamps, this is a classic ferromagnetic ballast, which is just an iron core coil with losses going up to 85%. And this ballast is not able to ignite the lamp. This ballast can provide 400 milliamps, stabilize AC current, but it is not able to provide 2000 volts to ignite the fluorescent lamp. This is an electronic ballast supplies the lamp at frequencies from 20 to 200 kilohertz, very higher efficiency, and you can include here an ignition sequence. And also you can include that we call the electrode preheating in order to reduce damage of the electrodes. This is not possible with that one. Let's speak about the starter. If you are using ferromagnetic ballast, you need an external circuit to ignite the lamp, and the oldest one is that we call a bimetallic stripe starter. Has that form. You can find either for fluorescent lamps inside the old fixtures, and you can find it also for some kind of high pressure lamps. And in fact, what happened, you have different phases. When you send the current in the circuit, initially the lamp is switched off. That means the current cannot pass through, but the circuit is then connected in parallel with the lamp. That means the voltage passes through the bimetallic stripe, and the bimetallic stripe, what is inside is a small discharge also. You have a gas at very low pressure, much lower than the lamp, and the distance between those two electrons here is very small. That means 200 or 100 volts, according to the country, are enough to create a spark here. And when you have the spark here, you close that circuit, and then one part of the bimetallic stripe will heat up due to the plasma and will change form and will touch the other electrode. When the two electrodes touches, the nature, like the way of the less losses, no need to keep the plasma inside alive because you have classic contact. Then the plasma disappears, but if the plasma disappears, no more heating. And then the bimetallic stripe will open and will come back to his initial position. And if here you have 400 milliamps passing, and this open in few microseconds, you pass for 400 milliamps to 0 milliamps, and behind you have a huge inductance that will respond with a voltage pulse that can go up to several thousand volts, and these several thousand volts will be in the electrodes, and your plasma can strike. Let's look here. I hope that the small video is working. If I found my, yeah, there it is. Look. Up, the plasma appears, the lamp is here. It closes and open, and then you have the lamp behind is ignited because the ballast here produced more than 2000 volt impulse in very short time, and this is enough to create the operation. I will show you again once. That is for a sodium lamp, but in fact I could not find a video for a fluorescent lamp. But if you wanted to show that to your students, you take an old fluorescent lamp with the standard setup. I have that for my students in Toulouse, and I took one classic igniter. I get out the cap, and you can see the device inside, and you can observe the phenomenon. Look again. Plasma, the two electrons touch, the plasma disappear, and the pulse goes to the lamp. Well, that was what we can do with, yes, that one, with ferromagnetic ballast and bimetallic stripe ignitors. but this is really legacy. You find it less and less around us, either in the buildings or in the cities. Today, for fluorescent lamps, we use electronic ballast that you have to define at which frequency you want to operate that ballast. And here is an example. If you stay between 20 hertz and 20 kilohertz, then you are in the audible zone. Your lamp may blinks and may also sound, which is not good. Then if you go between 20 kilo and 100 kilo, this is the best area to work. And now if you go above 100 kilo, then you have to redesign all your ballast and use a different kind of components inside in order to reduce the losses. And if you do that, the price becomes higher because you have to avoid different problems with switching frequencies and electromagnetic compatibility. There is what is globally in a such kind of ballast: a rectifier, a filter, come back there, and then a full bridge resonant inverter that finally will supply the lamp with a high frequency AC stabilized current. Well, this filter here can be passive capacitor, but if you want really to have a very nice stable current here for the DC, high quality DC, you need to put an active filter, and this active filter costs a lot of money. Use intensive IP, intellectual property, and for example, if you take a tridonic ballast, you will see that beyond all elements inside, you have ASICs, and inside the ASIC, you have the implementation of all the filter, the active filter, and some all other parts of the ballast in order to avoid to be copied. Okay. Now, of course, you can take the ASIC. Our Chinese friend can do that, reverse engineering, and they can cut the ASIC layer by layer and see what is inside. But okay. Why we need to have a very nice DC? For two reasons: in order to avoid to inject harmonic distortion in the mains, and also even if you send here high frequency, in fact you have variations due to the remaining voltage, DC voltage variation, and this will induce flicker in the lamp. Flicker at a frequency which is the double of the mains frequency. If you are in 50 Hertz, you will have flicker at 100 Hertz. If you are in 60 Hertz, you will have flicker at 120 Hertz. And the ignition, in fact, here you play a little bit with the circuit and the resonance effect. Initially, when the lamp is not ignited, here the impedance of the lamp is infinity because it's an open circuit, and then you have a frequency that you get the maximum voltage. And in fact, if you play a little bit with the frequency here, you can arrive at the maximum voltage. This maximum voltage is enough to ignite the lamp, and when the lamp ignites, now here the resistance is finite, has a value, and your curve changes. That now, if you play with the frequency here, the only thing that you do, you can do dimming of the lamp. You cannot go to so high values because you don't need it anymore. Well, the system is self-adaptive. We use it initially for ignite the lamp, and once the lamp is ignited, the system, playing with the frequency, the switching frequency, you can make you can make a dimming of the lamp. Well, The problem is if you stay at low frequencies, you have that we call the reignition peaks. That is, you pass from there to there. It's time that the current passed through zero, and this is a generator of harmonics in the other side that you have to filter, or you have to go to very high switch in frequency above 10 kilohertz, and then this green line will become also sinusoidal. And you observe what I said, the lamp, this is the voltage and current measure on the lamp. Here, you see that they are in phase. That means even if the lamp is a nonlinear resistor, a curious nonlinear resistor, is still an ohmic resistor, don't cause any phase shift between voltage and current. What I have here, yes. And this is when you arrive in a permanent regime at high frequency, then you explore the self-oscillating character of the ballast, and once the lamp is switched on, you can continue supplying the lamp. As I told you, sometimes for this kind of lamps, but also for high pressure lamps, if you don't send the right wave in the lamp, the right voltage, especially during the breakdown, you can cause evaporation that they are on the top of the electrodes. In fact, if you look at a fluorescent lamp, if you crack one, be careful, there is mercury inside. Don't do it inside, do it outside. You can cut, and you will see that the filament, to its size, they are two electrodes with a filament shape, and there is a white past on the top of those filaments. This white past, in fact, is contain three different kinds of oxides, and when you heat those oxides, they emit easily electrons. They have an extraction work for electrons very low compared to tungsten. That's because we put this emitting past, and the problem is if you evaporate all the emitting past, you are not more able to emit the initial electron swarm necessary to ignite the plasma. The way to avoid this rapid evaporation is to preheat the electrodes before the breakdown. And high-end ballasts, electronic ballast or drivers can do it. They can preheat the electrode in order to reach the right temperature the moment that the pulse for igniting the lamp will send to the lamp, and this can reduce the problems that are harming the lifespan of the lamp. And also you can go to very deep dimming levels because at very low dimming levels the electrodes have to supply much electrons, and there is the place that you vaporize more and more the emitting past. And if you keep the electrode hot enough, thanks to such kind of ballast, you continue respecting the lifespan of the lamp. Well, you see that was the problem because some years ago, when you buy a fluorescent lamp for one manufacturer, you can couple it inside a fixture with the ballast from another manufacturer. Okay? And if a manufacturer of the lamp says you that the lifespan of the lamp is 12,000 hours, if the ballast that you have inside your fixture not respecting the lamp operation, 12,000 hours is completely meaningless. Okay? You tell me also if I have electronic ballast also has a lifespan. Yes, but the convention, this is not a standard, it was a convention, is don't change the ballast before changing at least 3 times the lamp. That means if you have lamps with 12,000 hours lifespan, that was one of the best that we can find for fluorescent lamps, the ballast lifespan had to be at least 36 to 40,000 hours which is achievable. Yep. Yeah. And this is, finally, I will not comment that, a full structure of a self-oscillating ballast with electrode preheating. And you see that for a physicist like me, I want to have a stable AC current, a bridge, a filter, and then an oscillator or not. To the power electronics side, guys, this is something completely different. And you understand that each component that you add here and you change something, first of all, you have to look about intellectual property. Second, you have to calculate what is the additional cost that you add in your system. And this is also the possibility to regulate the ballast, do dimming, and it becomes more complex because you add you have to add a controller. Yeah, okay. This is can go fast. Nothing interesting here. And this is even best. You can have a dimming ballast with a high performance for all the stuff, and then you have to add the heating circuit. You have to supply all of that part and things like that. Okay, and this is just the implementation of all that stuff in a ballast that is 10-15 centimeters long, couple of centimeters large, and a couple of centimeters high, and has to not to be very very heavy either. And usually this kind of ballast, they have a double side PCBs. Okay, a few words about the LED drivers. The LED drivers in principle are simpler because that you need is to obtain DC current. That means LED require a reliable DC current source to operate. We can ask then what is the effect of non-perfect DC current for LEDs. The effect is you have if you have not very well filtered DC, you have a flicker, and the flicker here is much more noticeable because the LED is just a diode and can follow quasi instantaneously any variation of the current. A discharge lamp, you have thermal effects and somehow very rapid variations. You cannot see it with a discharge lamp. Well, the drivers have also a secondary function which is preventing power surge fluctuations, for flicker especially, and they are designed for use within a strict predetermined lamp range, amp range, yes. You cannot take a ballast that is assumed to provide 400 milliamps and use the same topology exactly if you want to have 3 times more. You have to redesign almost the ballast, but the big advantage is that all LEDs usually use for they are made for 600 milliamps current, and this amplifies the work. Different LED drivers. We are speaking more here about different architectures, and you can find, commercially speaking, different models, different types with different efficiency, different power ratings, and protections or not, shielding against electromagnetic effects and all that stuff. And of course, all that here will affect directly the quality and the price of the ballast. Then you have here 5 big families. You have drivers for small or mini LEDs that they are designed for small LED lights, like 4 watt, for example, maximum, or even less when you have a torch with a battery inside. You have always a driver behind in order to keep the light as constant as possible, whatever is the voltage of the battery during the discharge. Then you have dimmable LED drivers that allows to user to adjust the brightness and also adjusting the quantity of light or even the temperature has a direct influence on the mood on the atmosphere that you will generate with that lamp. Okay, and tomorrow we'll speak about automation, how you can command all these kind of things by using standardized communication protocols. Okay, you can have high power LED drivers. They are usually deployed in large lighting systems inside buildings or mainly in the cities. You have a driver for chip on board configurations that may include or not dimming function, and they have to be compatible with the different constraints imposed by COB LEDs. And finally, this is more for decorative aspect. You know, you have stripes with LEDs, that you have several LEDs in series, and then you need almost specific LED drivers to supply this kind of lights. And usually these LED strings, they are not expensive. That means here the quality of the driver is rather low. Well, various existing topologies to do all this kind of drivers. And you see here the main topologies that we use today is flyback, back boost or back boost, or AC linear. And you have different characteristics concerning isolation, efficiency, cost, harmonic distortion, what kind of current you can input, what kind of current or voltage you can get in the other side, and what are the main applications in the domain of lighting. If, for example, you take the back here, no isolation, high efficiency, low cost, good behavior concerning harmonic distortion, you can inject constant voltage or constant current, but you have voltage which is lower than the input one. That means if you deploy in your room 48 volt DC and you want to supply a lamp that needs 60 volts because the number of LEDs inside, this topology is not working. And this can be used, for example, to supply bulbs with integrate drivers, or T-light means tubes that can replace fluorescent lamps. Okay, that means the application can impose what kind of topology you have to use for that. And here I use only general lighting things. I am not speaking about festive lighting, dynamic lighting, nor about automotive lighting. Automotive, you have also LEDs, and the drivers, they can have different topologies. Just going fast, flyback, provide safety isolation, support wide range of output voltage, and they are better for harmonic distortion. Disadvantage is rather low frequency, large size transformer, and high cost. If I take back technology, high efficiency, smaller size of a power inductor, low cost, low voltage stress on the MOSFET. That means you may have higher reliability and lifespan, better behavior concerning electromagnetic interference, but the disadvantage that is you have limited input-output voltage ratio, and the output voltage cannot be higher than the input voltage. And this is a variation of back using a high power factor back converter. Well, this is you will have the slides. You can look it. Now, if you go to boost technology, the advantage is you have high efficiency, smaller size like before of inductor. This is the best one for harmonic distortion. The disadvantage is the output capacitor needs high voltage stress. And this is, can be problematic. And the output voltage cannot be lower than the input voltage. Okay, that's why boost. Back boost technology. Advantage, no input or output voltage ratio limit because you have both behaviors. You have a very good behavior concerning distortion, and the disadvantage is that you stress the switch. And just AC DC linear topology is very simple. No magnetic components, simple external circuit, that means low cost. Disadvantage, require high voltage output, maximum power is limited for thermal issues, and cannot support universal voltage. It's what I was saying, a bridge that could be 4 LEDs, and then some elements here. This one you can put it or not. If you have that, it's just to be able to make dimming, and then you have just but this is very simple. Frankly, it's not advised. Because your LEDs, remind, they are in a series. If one LED collapse, say that 85% in the case that an LED collapse as a closed circuit. That means you continue feeding the other LEDs, but in that case the current will increase, and if the current increase, a second, a third LED and so on will collapse, and then the current increase again, and so on. And 15% of the cases the LED can collapse open, and in that case you cut all the string and you lost all the light. To reliability point of view, not good. And this is the high voltage back technology, and that I think was the last one that I wanted to show you. That's all about ballast and drivers. I propose to have a break till 11:30, and then from 11:30 to noon, 11:30 to most probably I will see the time that we have. Maybe I will add something else, but the next sequence from 11:30 say to noon 30 or 45, I will spoke you about fixtures. Fixtures are more optical components, less near to your speciality, but they are also very important for the final efficiency of the system, and you have to understand when we speak about fixtures what is there. Okay? Okay, well, let's take 15 minutes break. Okay, Pradu.